Okay. We started talking about equations, and I know it sounds kind of simple right now, but this section actually turns into something that I think was like one of the more harder topics in this class. I don't know if we'll get to that yet, but there's something in this packet that is slightly difficult. So we'll do a lot of practice on that. So we talked about equations. They are things that involve an equal sign. So there are things that talk about two things that are equal. We talked about how to solve a very simple equation. If you want to do something to an equation, you have to do it on both sides, right? So you can multiply, divide, do anything as long as you do it on both sides. Once you get the answer is what we call a solution, or we say the answer satisfies the equation. We also talked about it's pretty easy to check if our calculated solution is right by just plugging in our solution into the equation, and if we get two equal numbers, then we're good. Okay, now there's different types of equations. One of them we'll call equivalent equations, and these are sets of equations that have the same solutions. Is there anyone who could give me an example of two equivalent equations? Okay, how about this one? X equals 2. Is there anyone who could give me an equation that has the same solution as x equals 2? What about 2x equals 4? Does that have the same solution as x equals 2? Yeah, right. So if we solve for x, then x would be 2. So this is an example of two things that have the same solution. And we call these two equivalent equations, okay? So whenever I talk about something like that, that's what we're talking about. All right, let's flip our page. Some other notation that we'll talk about is, okay, one thing, if I say to solve an equation in x, all that means is I want you to find all the solutions of the equation. Now, there's the word all, right? So equations can have more than one, less than one solution. So let's talk about that real quick. So sometimes an equation can have more than one solution. Any examples of an equation that kind of fits that category? Yes, we're on the back of page 1. More than one solution. I'm not going to pick on you, I promise, Winnie. What about this one? X squared equals 4. How many solutions does this equation have? 2, right? Because if you solved it, let's try to solve it. We would take the square root of both sides, and I will go over this later, but what am I forgetting when I take the square root? What do I need to add? See your hand. Perfect, a plus or minus sign, right? So x would equal plus or minus the square root of 4, or 2, right? So this is an example of something that has two solutions. Okay, I'll show you something else that you might see on your homework. I'm not sure though. What about this equation? 7 equals 7. How many solutions does this equation have? Not one. There's a little bit more than that. I think I heard it. Infinitely many, right? There's no x in this equation, so it doesn't matter what I plug into an x if it's not there, right? So any value of x that isn't there would fit this equation. So this is an example of something that has infinitely many. Infinitely many solutions. Okay. Now let's talk about something else. Sometimes an equation has no solution. So instead of more than one, it has no solution. Any examples of equations that have no solution? Well, we got 7 equals 7 here. Oh, Steven?
X squared equals 0.
Very, very, very close, but instead of 0, you should probably put a negative number. Good. X squared equals 0 actually does have a solution. It would be 0, right? But x squared equals, how about negative 7? Okay. If you try to solve this, right, you would take the square root of both sides. And of course, we'll go over doing this a little bit later, but x would be plus or minus the square root of negative 7. And if you typed the square root of negative 7 in your calculator, it would come up with something really weird. It'd say error. Okay. And this is an example of something, and we'll talk about what this actually means, of something that has no solutions in a particular set that we're used to working with. In particular, the real numbers. Okay. Yes. Yeah, so the reason I say the real numbers is because there are different types of numbers, right? And the real numbers don't include these things called imaginary numbers, which we'll talk about a little bit later, but that's a nice observation. But we'll definitely get into those imaginary numbers that trip us up a little bit. All right. I'll give you one more example of an equation that has no solutions. We have 7 equals 7, which of course doesn't have has infinitely many solutions. 6 equals 7, right? Is there any value of x that could make 6 equal 7? No, right? So this is an example of an equation that has no solutions. And no imaginary solutions either. All right. Okay, so let's keep on going here. We talked about types of equations. We have equations with different types of solutions. We have equivalent equations. I would say the most basic equation that we can write is called a linear equation. Linear has the word line in it, right? Line or equation. Can someone give me an example of a linear equation? Yes. Perfect. And we got to stick an equal sign, right? So equals, I don't know, 1, right? This is a linear equation because it has an x in it and it's not raised to any power. Okay, so the highest power of x is 1. If you graphed an equation that had 2 variables and you were trying to look at the correlation, it would look like a straight line. And in general, these equations can be written in this form: ax plus b equals 0. So we have a and b, which are just numbers, and we got an x in there. A can't be 0 because if it was, then there would be no x in the equation. Okay. All these equations will always have one solution. And let's just talk about how we can get to these solutions. Okay. So here's one example. We have 6x minus 7 equals 2x plus 5 over 2. What can we do to kind of help get x by itself first? I think I heard add 7. Add 7 would be interesting. Let's actually do it. You don't have to write this down if you don't want to yet. Let's say if we added 7, and it's okay to do stuff on both sides. It's not wrong to do this. 6x equals 2x plus 5 over 2 plus 7. Did this make it easier for me to solve the equation? No, right? Because I kind of made it more complicated, right? Now I have a fraction and something added to the fraction. So that's not going to really help us. Any other ideas? I'll pick on Allison. Yeah, so looking at this equation, the thing that's really making us confused or more confused is the 2 on the bottom. We don't like denominators, right? We like things being in the numerator. So why don't we first multiply by 2? Okay, so on the left-hand side, I'm going to have 2 times 6x minus 7 equals, and it looks like the 2's will cancel out, right? Numerator, denominator cancel out. And we're left with 2x plus 5 in the numerator. Okay. What should be my next step now?
Plus 6x minus 7 by 2.
Perfect, right? Now what's kind of messing us up here is the parentheses. That's making it more complicated, right? So why don't we move this 2 or multiply the 2 inside the parentheses so we can make things a little bit more expanded. So we're going to be left with 12x, right, minus 14 equals the right-hand side. Okay. Now, what we really want to do is we want to get the x's on one side and maybe the numbers on the other side, because that might help us be able to divide out by the constant on x. What should be our next step now? Multiple things we can do. Awesome. Yeah, add the 14. Another thing you could do is subtract the 5, but adding 14 might make things more positive, so that's a good step. That's a good idea. 12x, the 14s cancel, right? So that cancels out. Equals 2x, 14 plus 5 is 19, right? Good. I'm not very good at mental math, so it's good that I have people to check me on that. All right, next step. Yes. Perfect. Subtract the 2x on both sides. Okay. On the left-hand side, I'm going to have 10x, right? On the right-hand side, looks like the 2x's cancel out, and we got 19 on the right-hand side. What should be my last step?
Divide both sides by 10.
Perfect. Divide both sides by 10 because we want to get x by itself. Oop, put x there instead of 10. And our final answer looks like x equals 19 over 10. Okay. Oh gosh. Any questions? Yeah, that's totally fine. Yeah, decimals, fractions, totally fine with me. Any question on example 1 or any other questions? Nice. All right. Here's another one. This is a linear equation. You might not see it at first, but you'll kind of understand why it's linear as you go along. I'm going to give you a few minutes and you can work together if you would like to. I'll give the other half of the room some attention next time. All right, so Logan wrote out a perfect answer here. Do you kind of want to take us through what you did here?
I just loaded and then just canceled out the term until I got x. I on one side and just by that.
Perfect, right? So let me go through it a little bit more detail, but that's a great answer here. The first thing Logan did was he FOILed, which meant he expanded out these multiplied terms. Unlike the last example where we had to multiply by the denominator, we don't have a denominator here. So the thing that's making things more complicated is really that we have multiplied parentheses of groups of terms, right? So the first thing you might want to do is multiply across on the left-hand side and FOIL or expand out the right-hand side. One thing that I saw a lot by walking around is when everyone did 8x times 3x, some of you wrote 24x and not x squared. So when you're multiplying out these terms, make sure that you also multiply the x's as well as the numbers. Okay, once we got here, you could pretty much add and subtract anything that you'd like on both sides. You didn't have to add specifically the 8, you could have done the 3. But once you've gotten everything on one side and the x's on the other side, you should have gotten 5 over 12. Any questions on example number 2? Okay. All right, so I have some examples of this on the homework, I think homework 2. If you're feeling a little shaky on these guys, I'm gonna put some examples on the ungraded homework assignments or the extra credit stuff. So if you're feeling a little shaky, just do a couple examples or come to me. And we're gonna talk about something a little bit more hard. We're kind of easing our way into this. Okay, here we have an example where we have fractions, but the fractions involve variables now. So we have x's in the denominators. This is where things get a little bit tricky, okay? Does anyone know what a fractional polynomial is called? Like a polynomial over a polynomial. These are called rational expressions. Okay, and all that means is we have a polynomial over a polynomial, okay? So poly over poly. Okay. So I guess the 6 over x plus x minus 2 is also a rational expression, okay? We're gonna talk a lot about how to solve equations that have rational expressions. It gets kind of tricky, so let's go through this more simple one, and then we'll talk about a whole process to go through when we do these. Okay, checking on time. Good. Okay, looking at this equation, what do you think we should do on both sides first, Stephen? Good, right? That seems like a good idea. Just like we had 2 in the denominator on the first equation that we solved today, x minus 2 is in the denominator, so maybe we should multiply both sides by x minus 2, okay? So I'm gonna do that. I'm gonna do x minus 2 times 3x over x minus 2. And then we've got 1 plus 6 over x minus 2 times x minus 2. Okay. And this will surely take out the denominator, okay? What we are essentially doing is we're multiplying by this thing called the least common denominator. Common. Okay, and we'll talk more about what this is, but essentially it's the least thing that we can multiply both sides of the equation to make sure the denominator goes away. Our goal is to kind of take out that denominator. Okay, so multiplying on the left-hand side, we can easily kind of cancel out the numerator and denominator here, and we're definitely left with 3x on the left, right? Okay, on the right-hand side, what should I do? Yes. Perfect. I'm gonna take it a little bit more step by step, but good job there. Essentially what we're doing is we're just multiplying this group of things by each of the terms in our parentheses. So essentially we have x minus 2 times 1 plus 6 times x minus 2 over x minus 2. Everyone good with me so far? Good. Okay, so I just multiplied the x minus 2 to both terms. Okay, on the left-hand side, looks like we have 3x still. X minus 2 times 1 is just x minus 2. And the last term, we can definitely cross out the x minus 2 on the top and the bottom. Then we're left with 6. Okay. Looks like we have some like terms here. So I guess we can combine this -2 and the +6. And I think we're left with 3x equals x plus 4. Okay. What should my next step be? Stephen? Yeah, subtract x from both sides. We really want all the x's on one side, all the numbers on the other side, so we can divide out by the coefficient of x. So let's subtract x on both sides. We've got 2x equals 4. Okay. And I guess all we have to do is divide by 2 on both sides, right? To get rid of that 2. And x equals 2. Okay. So we've done our work. We've got that x equals 2. Why don't we check our work? Let's see if we have the right answer. How do we check our work again?
Put 2 for X.
Yeah, we plug in 2 for X, right? So awesome. So let's do a little check here. Let's check. Okay, so I'm gonna take my equation and every time I see X, I'm gonna write 2. So we've got 3 times 2 over 2 minus 2 equals 1 plus 6 over 2 minus 2. Okay, so just plugging in. All right, on the top we've got 6 over 0 equals 1 plus 6 over 0. Uh-oh. What's the problem here? Yeah, they're not equal, and also we're dividing by a 0, right? Yes?
I was gonna say that 6/0.
Yeah, 6/0 doesn't actually exist. Now, a lot of people are going to say that 6/0 equals infinity. It does not equal infinity. If you take a class called calculus, you'll talk about limits, and that would be infinity. But 6/0 does not exist. Okay, so this is something that does not exist. And this equation basically kind of falls apart because we have numbers that don't exist in it. This equation that we're doing just isn't going to work at all. Okay. So is oh my gosh, is X equals 2 a solution to my equation? No, right? So the thing that we found is actually not a solution to my equation. Okay. Now, essentially what happened is we have an equation, okay, and we'll talk about this thing called domain and range in the future. You probably heard about these. X equals 2 is actually something that isn't even in the domain of this equation. It's not even something that this equation will take on. This equation doesn't even like X equals 2 at all. So we're just going to scratch X equals 2, and this equation actually has no solution. Okay. Okay, so we did this equation, we did everything right, but it turned out that one of our solutions didn't actually work. Let's try to figure out what happened here, okay? So question I wanted to ask was, what made the question different from the other? This question had a rational expression. It had a polynomial in the denominator, right? So this was a rational. It had X in the denominator. Okay. And one thing I also want to point out is we had 2 equations here. We had 3x over x minus 2 equals 1 plus 6 over x minus 2. We did a little bit of work to this equation. So we had this equation up top, and we also did a little bit of work and got to this equation, right? So 3x equals x minus 2 plus 6, right? So that kind of turned into this equation. Okay. One thing that we'll talk about a little bit later is these 2 equations, even though they look the same, we did work to get from one side to the other. These 2 are not the same equation. And when I say that, I mean they're not equivalent equations. Okay, so even though you did some work to get from one to the other, they are not equivalent because the one on the right has x equals 2 as a solution. The one on the left does not have x equals 2 as a solution. And we'll talk about why these 2 are not the same a little bit later in the class. So just something I want you to think about. Okay. Any questions before we get into a little bit more complicated rational equations? All right. If we flip our page, okay, I define rational expressions. We're going to talk about that. I'm going to go back to that thing that we labeled the least common denominator. Remember, that was the smallest thing we can multiply on both sides to cancel out the denominator of our equation. And the term least common denominator comes out even in just adding regular fractions. So let's just, I know we love fractions. Why don't we add these 2 fractions here? Okay, we got 2 over 5 plus 1 over 6. And I want you to leave some space down here. I know it's not much. Okay. When I add these fractions, you always want to find what's called the least common denominator, or the two denominators that you're going to add together at the end. What's the LCD in this example? Yes, 30, right? You basically took 6 and 5, multiplied them together, and we know that, okay, the least thing I can do, or the easiest thing to do, is to make both of these fractions a fraction over 30, so I can add them together, right? Okay. 2 as a fraction over 30 is 12 over 30, right? And 1 over 30, or 1 as a fraction over 30, it would be, gosh, 5 over 30, right? So if we added these together, we would get 17 over 30. Okay, so that's one thing we can do. I'm going to show you something else that happens with LCDs that make things a little bit more tricky. Let's add 2 over 10 plus 1 over 6. Let's do that. Okay. What's the LCD now, Stephen? It could be 60, but I'm going to tell you there's something lower. It's still 30, and why is that? Because it's the least common denominator. Now, the reason it's still 30 is because 10 is not a prime number, and 6 wasn't either, but it didn't share any factors with 5. If I factored 10, it would be what? 4 times, oh God, wow. It's 2 times 5, right? Okay. If I factored 6, it's 2 times 3, right? So the reason the LCD was 30 was because I can multiply the 2, the 5, and the 3, but I don't need to multiply 2 again because I already accounted for it with the 10, right? So the least common denominator is actually taking all the factors that they don't share already and multiplying them together. Okay. So LCD is still 30. Let me see if I can translate these fractions into fractions over 30. 2/10 is 6/30, I think. 6 over 30, all right. All right, and 1/6 is 5/30. So this would give us 11 over 30. So we have this thing called the least common denominator. Usually we can just multiply everything in the denominator, but if they share a certain factor, then we don't need to account for it again. We can just count for it like once. Okay. Let's talk about, let's kind of take a step back from this and go to rational equations. Okay, we got this example. We have 1 over x plus 5 plus 1 over x plus 3. Oh gosh, x minus 3 equals 2. We're not actually going to solve some of these. We're just going to talk about the LCD. What would the LCD, or the smallest thing I need to do to multiply on both sides to cancel out the denominator? What is the LCD here? What would I multiply on both sides of this equation first? Yes. Not quite. Let me do an analogous example here, okay? What if this was 1 over, let me do 1 over 4 plus 1 over 3. Let's just do 5 and 3. Let's just do that. 1 over 5 plus 1 over 3 equals 2. What would I multiply on both sides now? Grace? Perfect. So I could literally multiply both sides by 3 times 5, right? And that would ensure that the denominator would be canceled. Does everyone kind of see that? Okay. Any guesses on the fractional exponent this time? What should my LCD be? Stephen? Perfect. X plus 5 times x minus 3. Okay. So just like we did with fractions, the LCD is just multiplying together the denominators. And we don't have any like repeated stuff going on yet, but this is what we do with LCD. multiply together all the denominators. Okay. Okay, let's say we did all the problem, we finished the entire problem, and we're checking to see if our answers are actually solutions to the equation. What do you think I can't have as a solution to this equation? Yes. 5 and 3, and why would that not be a solution?
Zeros.
Yeah, right. 5 and 3 are definitely things that if we plug into this equation, the denominator would be 0, and well, you can't divide by 0, and you would just kind of have a messed up equation, right? The way I got 5 and 3, you can kind of just look at the equation. An easier way to do it, or more systematic way, is to take each component of our LCD, x plus 5, x minus 3, okay, and set them equal to 0. Okay, so we're basically taking all the denominators of our equation, setting them equal to 0, and seeing what values of x happen. Okay, solving x plus 5 equals 0. Oh gosh, you can subtract 5 on both sides. X can't be negative 5. You can add 3 on both sides. X can't be 3. Okay, these two are things that can't be solutions to the top equation. Okay. Any questions so far? Okay. I think we have enough time for another one. Let's go to example 6. Okay, here we have a big one. And there's a reason why we're not actually solving some of this, because solving this would take a lot of time. But we have x over 2, x plus 5, plus 3 equals all this mess over here. Okay. Let's talk about what we can make the LCD. Any guesses? Grace? Definitely the 25, so the x plus 25, right? Good, so x plus 25 definitely should be in the LCD. Anything else should be in there? X minus 2 definitely should be in there, right? So I counted for that in the denominator. Okay. Anything else? X plus 5, good. X plus 5 should be in there. Okay. What else can I put? A 2, okay? So I counted for that. Should I put the other 2 there? No, right? Because I already accounted for it in the left-hand side. I don't need to repeat it because then it wouldn't be the least thing I need to multiply on both sides to cancel out the denominator, okay? So I only need to write the 2 once, okay? Only need this once. Okay, and we're accounting for every single factor in the denominator. Okay. Let's talk about what can't be solutions. I know you can kind of do this in your head, but if you need a systematic way to do this, you can take each component of our LCD and set it equal to 0 and solve for x, right? So we've got 2 equals 0, x plus 25 equals 0, x minus 2 equals 0, and x plus 5 equals 0. Okay. How many solutions does 2 equals 0 have? None, right? So this kind of just goes away. We don't need to think about that. Solving for x on the other ones, we can subtract 25 on both sides. So x equals negative 25, x equals positive 2, x equals negative 5. These are the 3 things that cannot be the answer to my equation up top. Okay. Any questions on example number 6? I don't think I'm understanding your question. Can you kind of
Like on the, how we said, if we x 2, for example, the x minus 2.
Oh, yeah, but x equals 2 is here, right? Oh, yeah. Sorry, my handwriting's kind of messy. Okay. Did that answer your question? Positive 5, I could actually plug in. Yeah, I could plug in positive 5, right? Yeah, do you have another question? Okay. Any other questions on example 6? Perfect. Okay, taking a look at the time, I think it's about quiz review time. So why don't I stop this? If you're on Zoom and you're looking for the quiz review, go to the modules page and scroll down and you'll find it here. But for those of you here, I have it printed out for you.